So one thing I should just clarify, which came up yesterday, is G of tau. We have theta 2 so this is the definition of G of tau. So we need this cube to get this in the model function. Okay, so yesterday we started our discussion on elliptically fibered K3, and we also worked out the specific description of elliptically fibered K3. Okay, so let me remind you what the description was. So essentially we describe it by a surface of the following form. Okay, I have now gone back to the inhomogeneous coordinate z of the plane. So f of z is a polynomial of degree 8. G is a polynomial of degree 12. So we have three complex variables, one equation, so that gives you two complex dimensional space, and that we said is elliptically fibered K3. Okay, we discussed why the first giant class vanishes for this. Associated with this, the tau of z is determined by solving this equation. G of tau of z is 24 f cube times 4 over 4f cube plus 27 g square. Okay, so once you know f and g as a function of z, you can calculate g of tau as a function of z, and that determines tau of z up to Sn to z monotone. Okay, and today we will try to solve it in special cases where we will also pick some Sn to z monotone. Okay, then we looked at some special examples. F of z, a times product I equal to 1 to 4, z minus zi square, g of z is b times product I equal to 1 to 4, z minus zi cube. So these are indeed homogeneous polynomials of degree 8 and 12 respectively, okay, but special ones. They are special because when f and g are chosen this way, we can see that g becomes constant. So g of tau of z becomes 4 times 24 cube over 4 plus 27 b square. So tau becomes constant on the sphere, on the base. Okay. And we said that we will prove today that this is the orientifold. Okay, so we'll now go ahead and see how we can prove this. Okay, this is not orientifold in any configuration, but we said that this will be identified as orientifold, where on each of the 4 orientifold planes there are 4 d7 planes. Okay, so the charge is locally cancelled. Once the charge is locally cancelled, tau can be constant. Okay, otherwise tau cannot be a constant, right? Around a single d7 plane, we have seen that tau has this form of 1 over 2 pi I log of z minus z naught. Okay, so tau cannot be constant, but once the d plane charges are cancelled, okay, it is possible for tau to be constant.
So what about the contradiction that if tau is constant, then the base manifold should be a Calabi-Yau, but here it's a sphere, which is
okay, we'll see what the base manifold is, okay, right? Because we'll calculate the metric on the base manifold, okay, and we'll see what it is. So indeed the base manifold is not Calabi-Yau, okay, but it's closely related to Calabi-Yau.
So
yes.
for a given value of a, I mean, it can turn out that J is infinity. So the base manifold will be
Yes.
V.
So J will be infinity when this is 0.
Yeah.
Right?
So it will be, the base will be V coupling throughout.
Yes. In that case, the base will be coupling throughout. Right? In particular, you can make this to be as small as you like. Okay. And in which case, the coupling will be small everywhere. Okay. When you do a more general case, that's the strategy we will follow. Okay. We'll try to make the coupling small in as much in most of the places. Okay. But right now we can choose a general term and proceed. Okay. So the first thing we want to do is to see what is the monodromy around the point z equal to zi. Okay. So what is the picture here? We have a base which is a sphere. Okay. There are some 4 spatial points on that base. Okay. Even though tau by itself doesn't depend on that base, clearly z equal to zi are spatial points. Okay. And we will see that those spatial points have spatial properties. So the first question we ask is, how do fields transform as z goes around zi? So z is the coordinate on the base, we should keep in mind.
I'm a bit lost. So
Yes.
if there is some given chart, this tau is multiple. When we come back, there is some monodromy.
Yes.
So here,
Tau is constant, so tau has no monodromy. But tau now having no monodromy does not mean that the monodromy is trivial, because -1 could leave tau unchanged, right? We had said tau goes to a tau plus b over c tau plus d, right? So if ABCD is diagonal -1, then also tau will come back to tau. Okay? So we know that the monodromy has to be either identity or minus the identity, okay? Because tau is constant. Okay? Those are the only 2 monodromies which are consistent with tau being constant. Okay? But at present we don't know whether it's plus identity or minus identity. Okay? That's the first thing we are trying to figure out. Is that clear? Okay. So for this, let's go back to this equation. Okay, we'll go back to the full K3. Okay. And you want to understand how does the fiber torus transform as we move on the base, okay, 2 pi around any of the points z1, zi. Okay. So suppose z equal to z1 plus some epsilon equal to I phi. Okay. Epsilon is a small number, which basically means that we stay close to z equal to z1. Okay. Keep some fixed small number epsilon, okay, and just change phi from 0 to 2 pi. That corresponds to a small loop around the point z1. And what you are going to do is to continuously follow the points on the torus. What happens to the points on the torus as you move on the base? Okay. In order to satisfy this equation, the point on the torus will also have to move, right? Because the same point may not satisfy this equation, right? If you change z, okay, and keep x and y unchanged, it will not satisfy this equation, right? So you want to change z, okay, and see how could you change x and y, okay, simultaneously to satisfy this equation. Now one way to do this will be to notice that if z takes this form, see, if at z equal to z1 is 0, right? Okay. So f of z will be some constant k1 times epsilon square into the 2 I phi plus higher order terms, order epsilon q, which you can here. Okay, because the leading term will come from the z minus z1 whole square factor, that gives the epsilon square equal to 2i5. Then z minus z2 whole square will give further corrections, okay, which I have not included. So this is how to get to leading order. Similarly, g of z would be some other constant k2 epsilon cube into the 3i5 plus order epsilon cube epsilon to 4. Now we see that
There was epsilon to the 4, right?
Pardon?
Ordered epsilon to the 4 for instead also. The correction because
no, because it is z minus z1 whole square, right? Z minus z2 is finite near z equal to z1, right? So the only small number is z minus z1.
yes, but then it's squared.
It's square, so that's the epsilon square into the 2i5.
Yes, no, that correction. That's
Oh, correction.
cube or epsilon.
Let's see. Correction may become of order cube also because z minus z2. See, if you take z minus z2 square, right? Then that will be like z1 plus epsilon into the i5 minus z2 square.
Okay.
So when you expand it out, you will get order epsilon term also here. Okay. Now suppose for phi equal to 0, we have a solution. Okay, now from simple scaling, we can see that because this goes as epsilon square and this goes as epsilon cube, okay, for this solution x will be of order epsilon, x will be of order epsilon, sorry, this goes as epsilon square, this goes as epsilon cube here. So f will be of order epsilon, sorry, x will be of order epsilon and y will be of order epsilon square. So the solution will be x equal to epsilon x1 1 equal to epsilon to the 3 half 1 then we call it x hat and y. Where y hat square equal to x hat cube plus k1 x hat plus k2. So these are all higher order corrections which will not worry. Is it clear what we are doing? We are saying that let's suppose that we have chosen y hat and x hat to satisfy this. Okay? If y hat and x hat satisfies this, then the claim is that x and y, once you choose x and y to be of this form, it satisfies the corresponding equation for phi equal to 0.
Near z equal to z1.
Near z equal to z1, yes. That's why our added plus order epsilon square higher order terms here.
I'm a bit confused.
Yes.
Why is it multiplied and not added? It should be something near x hat. Why should be something near y hat?
What?
No, I'm getting it.
Okay, x hat and y hat are by definition solutions to this equation.
Okay.
Okay. Suppose you have got solutions to this equation.
Okay.
Now the claim is that this is a solution to the original equation for phi equal to 0. Calculate y square, right? Let's substitute in the original equation.
Oh, sorry. I thought it is nearby.
Oh. So y square will be epsilon cube y hat square, right? We want to check this, okay? Equal to x cube will be epsilon cube x hat cube plus f of z we already know is K1 epsilon square times epsilon x hat plus G
K2 epsilon cube.
K2 epsilon cube. Okay, so epsilon cube cancels from both sides and you get y hat square equal to x hat cube plus Q1 x hat plus K2. Okay, that's what I said. So as long as this equation holds, this solves the equation that you want. Okay, for phi equal to 0. But we can in fact do more. We can also solve the equation for general phi. So for general phi, the solution is x equal to epsilon e to the I phi x hat, y equal to epsilon e to the 3/2 I phi times y hat.
Epsilon to the 3/2.
Epsilon to the 3. Right, because both sides just get an extra factor of e to the 3 I phi. Okay, e to the 3 I phi, e to the 3 I phi, e to the 3 I phi. Okay, so they just cancel. Is this clear? So given this, now we can ask what is happening to the points on the torus when phi goes from 0 to 2 pi. Okay, that corresponds to moving around in the around Z1, one full circle. Okay. So as you do this, what is happening to the fiber? Okay, what is happening to the torus? And you can see that if phi goes to phi plus 2 pi, then essentially x goes to x and y goes to minus 1. Okay, because of the 3/2 sitting here. So on the torus, we make a transformation, y goes to minus y. But that we have learned yesterday, that is exactly the SL2Z monodromy, which is -1, -1. Right? Y goes to minus y in the usual flat coordinates is w goes to minus w, and that in turn is the SL2Z monodromy. So this corresponds to SL2Z transformation. -1, 0, 0, -1. Is this clear? Okay, so what you are learning is that as you move around Z1, okay, or any of the Zi's, okay, once, in that process you make an SL2Z transformation on the torus, on the fiber torus, okay, which is -1, -1, okay, which basically means that from the type 2B viewpoint, of course, the fiber torus doesn't exist, okay, but SL2Z transformation has a real meaning. Okay, the fields will get transformed by this -1, -1 transformation. Yes.
So in this C0 doesn't change. So does it mean that we have conservation over all roots, all the zeros?
Because tau is not changing, because we have seen that tau, if you had a D7 brain, right, then as you go around it, tau should go change by 1. Right? Nothing is changing here, right? So that means the charge is locally cancelled. Right? And that's the reason why, if it has to be compared with the orientifold at all, right, the only point in the moduli space of the orientifold which has this property is when 4 D branes are on top of each orientifold plane. Right? We still haven't proven that it is orientifold, but if it is orientifold, it has to be at that point in the moduli space. Right? It cannot be in any other point in the moduli space, because then tau would have to change. Okay, but this is the first property of the orientifold that we had seen, okay? Because orientifold by the when all the D branes, 4 D branes sit on top of an orientifold plane, we had seen that you basically pick up a monodromy which is -1, -1. right? The minus 1 to the f left times omega, right? That's the transformation that you make as you go around the orientifold plane, right? And that minus 1 to the f left times omega is the transformation minus 1 minus 1. So at least that property of the orientifold plane holds. Okay. But now we have to check the second property of the orientifold plane. Okay. On the orientifold plane, okay, the compactification manifold was a tetrahedron. Right? T2 mod Z2. Right? Was a tetrahedron with 4 fixed points being the 4 vertices of the tetrahedron. Okay. So now you have to check that the metric on the base that we get has that property. Okay, that in that metric, what you are thinking of as a sphere, okay, is actually a tetrahedron. Is this clear? Okay, and that will also make it clear why the base is not Calabi-Yau. Okay, it's not Calabi-Yau, but it's an orbifold. It's an orbifold of a Calabi-Yau, right? Because you are taking, you compactify type to be on this T2, which is a Calabi-Yau, and then you make an orbifold, right, or orientifold. Okay, so it's not a Calabi-Yau, but it's an orientifold of a Calabi-Yau. Okay, so let's look at the metric on the base, and for this I have to write down the form for the metric in general, okay, and then take the limit. So for general f and g, yes.
I'm sorry.
No. Yeah.
In the denominator of the zeta function,
Yes.
using the special case, we found that it would be some I1 to 4 and then z minus zi raised to 6.
That's right. Yes.
So that means there are 6 objects sitting at each zi.
That's right. Yes.
And you said there are 4 d7 and 1 orientifold.
Yes. So we'll see that actually the orientifold plane corresponds to 2 objects. Okay. That we'll see later. Right? But indeed, so this connection, okay, is being made only at the spatial point. Okay. So you cannot really count how many objects there are. Right? But from the F theory viewpoint, there are 6 objects. From the orientifold viewpoint, there will be 5 objects. Right? 1 orientifold plane and 4 d planes. Okay. But we will see later how to reconcile this. Okay. Right now we are just comparing at the spatial point.
Similar technique would not work if this f and g would not have the same form, I mean, same roots.
Yes, exactly. Okay, then of course tau will depend on z. Right? Only in the spatial case, when f and g have the same form, same roots, that tau becomes constant. Okay, so in the orientifold plane, from the orientifold viewpoint, right, there is a unique point in the moduli space where tau becomes constant, where all the d7 branes, the 4 d7 branes lie on an orientifold plane. Okay, this is a moduli space of d7 branes, right, where the moduli is the location of the d7 brane. So from the F theory viewpoint, again, there is a more or less unique point in the moduli space, which is when f and g have this spatial form. Okay, the form is not completely unique because zetas can change. Okay, because the F theory moduli, okay, counts not only d7 brane moduli but also part of the metric moduli. Okay, that we'll discuss later. Once you make this connection, it will probably also automatically become clear. Okay, so for general f and g, we had defined delta, which was the denominator, which is 4f cube plus 27g square. This is a polynomial of degree 24 of degree 24, and hence is proportional to alpha equal to 1 to 24 z minus z alpha, and there is a constant of proportionality. Okay, and one can also construct g of tau z from here, okay, which is 4 times 24f cube over 4f square. In any case, given this tau of z, one can plug it into the Einstein's equation, okay, the equations that we wrote down earlier, and solve for the metric. Okay. Now this of course has to be done iteratively. Okay. That you have to first look for tau, then solve for the metric, but the metric will have its own back reaction, right? So tau configuration will change. Okay. But assuming that the coupling is sufficiently small over the base, we just do it once. So we take this g of tau and use it as a source and see what metric it produces. Okay. Afterwards we can try to correct it, but we will not try to do this now. So what one finds is that if we take a source of this kind, okay, where tau is varying as a function of z, then the metric that one gets on the base has the following structure. The metric that one gets is after a constant of proportionality. Okay, so this is the metric that solves this. What is tau? Tau 2 is just imaginary part of tau.
Can you repeat how knowing j as a function of tau and ultimately as a function of z?
Yes.
One gets this?
Because now tau of z acts as a source of the metric. Right? In the Einstein's equation, you have the del m tau del m del n tau bar, right? In the TMA expression. Right? So you compute that energy momentum tensor, put it back in that equation, and solve for the metric.
This is after that.
Pardon?
This is after that.
Yeah, this is after that. Okay. Now, I had told you earlier that tau by itself is not uniquely determined, right? Because g of tau doesn't determine tau. It determines tau only after modular transformation. Nevertheless, this combination is modular invariant. Okay, one can check that this combination is modular invariant. So it doesn't matter what modular representation you choose. Okay, this is well defined. Okay, otherwise you will be in trouble, right? Because by going to different modular representation, you cannot change the metric, right? Metric is modular invariant. The metric doesn't transform under SL2 set. This is the canonical Einstein metric. And the reason that that doesn't bother us is because this combination is modular invariant. So this one typically varies over the base. Now one important point we can see from here, okay, maybe that I discuss that first, that as z goes to infinity, okay, suppose infinity is a regular point, so tau goes to some finite value at infinity. In fact, it is a regular point because the tau goes to I infinity, the irregular points are that the zeros of j, of the denominator, right? And all the zeros are at z alpha anyway. Okay, so that we have taken to be finite. So infinity is a regular point, the tau goes to some finite value. So basically, as z goes to infinity, if you want to know the behavior, you can just look at this part. It goes at dz bar over mod z to the 4. Or I can also write this z square z bar square. And this is good because if we now make a change of coordinates that make you use a regular coordinate system at infinity, right? That's y, right? Z equal to 1 over y, say, or 1 over, let's call it z tilde. In that coordinate system, this just becomes dz tilde mod square. okay, which says that infinity in this metric is just a regular point, which is good because that's when the base is a sphere. Right? Otherwise, the base wouldn't be a sphere. Right? When I say the base is a sphere, that means infinity should be a regular point. Okay? Not only in terms of complex structure, but also in terms of the metric. Okay? And indeed, it is a regular point because there are precisely 24 zeros. Okay? If there are less zeros or more zeros, okay, infinity will not be a regular point. Is this point clear? Of course, you can make infinity an irregular point by sending some of the z's to infinity, but that's okay. Okay, because nobody says that the z alphas all have to lie at finite value. But there you understand why it is an infinity, because that's why one of the these level branches is sitting. Okay, so that's why it's singular.
So don't you have jazz sources and cow?
Yes.
Definitely.
Then this will have to change.
Yes. In present case, you only taking account D7, right?
Yes, except that when we saw, when you wrote down the equations, that the equations decouple, right? And even if you have fluxes and other objects, right? The metric equation, after appropriate scaling of the metric, is sensitive only to the source from the towels, right? So even if there are other sources, right, they don't appear in this form of the metric equation. Right? For example, fluxes etc. cancelled, right, when you took appropriate linear combinations. So you don't really have to change this. Okay? You have to change this, of course, because this is only first order, right? You have to keep iterating this. Okay? But you don't have to change this because there are other things in the other sources. Okay, now we are in business, so now we'll go to the spatial case. So group 6 z alphas to some zi. Okay, so instead of having 24 z alphas all different, okay, for the spatial f and g that we have chosen, right, they are grouped 6 at one go. Okay, so that means this sum will now over 1 to 24, so ds square will be proportional to d z dz bar over product I equal to 1 to 4, and each of these will be raised to 6th power because 6 z alphas come together, so z minus zi to the half z bar minus z bar I to the half, and also this has now become a constant. Right? Tau 2 has no z dependence anymore. That's what we saw, right? The tau becomes a constant once you have chosen the spatial form of f and g. Okay? So time is constant. And this is something we have seen before. Right? This is the metric on the tetrahedron. Right? If you took the flat metric on the torus and took an orbifold, then the natural coordinate on the orbifold is not w, but so I think we said w is now z square, right, around each locus. So dw mod square basically becomes proportional to dz mod square over z to the half z bar to the half. Okay, and then you put together the 6 with the 4 orbifold points to write down these as a metric of tetrahedron. Okay. So what you see is that from the starting from F theory, okay, in this spatial limit, the base points, okay, the 4 points zi can be identified as the vertices of a tetrahedron, and with that identification, the base, which is a sphere, really becomes a tetrahedron. Okay, so topologically, of course, it's still a sphere. It's just that the curvature has been concentrated at these 4 corners. Is this point clear? Okay, in a general situation, okay, the curvature will be distributed. Okay, while it will be distributed, first of all, it will be distributed at these 24 corners, 24 points. But also, tau 2 is not a holomorphic function. Right? Tau 2 is imaginary part of tau. Right? Tau was a holomorphic function of that. This is not a holomorphic function. So even in the bulk, there will be some curvature. Okay, if it has just a holomorphic function, then there will be no curvature because this you could remove locally by redefining your z. But this is a non-holomorphic function. Okay? So there will be local curvature, which is not surprising because once tau varies as a function of z, there is a local source of energy momentum tensor, right? Everywhere on the sphere. Okay, so you don't expect that you have flat sphere. But in this spatial limit, okay, you have this feature.
The 6 Z alphas denote 4 D7 brains and 1 oriented brains.
Yes. So it's not 6, 4, there are 4. Yeah, 6 Z alphas together. So 6 Z alphas together should denote 1 orientifold plane and 4 D7 brains. Yes, indeed. Okay. So this is something which I asked before, that it looks like from the F theory perspective there are 6 objects. From the orientifold perspective there are 5 objects. Right? So how can we reconcile the two? Okay, so we don't have to reconcile as yet because we have only considered the spatial case where they are all on top of each other, right? So instead of thinking of them as 6 objects, we really think of it as 1 object, okay, both in the F theory and orientifold. Okay. Once you split, we will see how to reconcile this.
So in total we have 4 orientifold planes?
Yes, so in total you have 4 orientifold planes and 16 D7 brains from the orientifold perspective. Okay. From the F theory perspective, we have 24 objects. Right? Whether they are D7 brains, we don't know yet. Right? We will study them as we go along. Okay. Now, from this perspective, from here, you can also see, okay, that F theory compactification, okay, contains more information than just the locations of D7 brains. Right? If you compare the moduli space of orientifold and moduli space of the F theory. Right? In orientifold, once you say that all the 4 D7 brains are on top of an orientifold plane, they are not positions of the D7 brains altogether. But there is moduli of the torus. Right? The original torus on which you compactify, whose orientifold you took, okay, that torus had a complex structure. Okay? That torus, well, it's not tau, let's call it rho. Okay? Tau we are thinking of as axial relator modulus, but that torus has a complex structure, let's call it rho. That is the modulus. So where is that modulus hidden in F theory compactification? That modulus is hidden in this coordinate zi's. Okay? Where the fixed points are on the tetrahedron. Okay? Here it looks like 4 complex variables, but of course SL2C, by making an SL2C transformation on the base on the sphere, you can make this 4 into 1. So there is only 1 complex variable worth of information in the locations of the zi's, okay, and that contains information about the complex structure of the base, okay, or not complex structure of the base, on complex structure of the torus before orientifold. Okay. So F theory data contains that information as well, okay, part of the geometric information, not just the information about the locations of the D planes. Right? From the orientifold perspective, you think of them as very different objects, right? Because one is closed string modulus, right? The tau, for example, is a closed string modulus, right? Whereas the locations of the D brains are open string variables. So F theory perspective, they will all come in the same data. Okay? That's the data that is hidden in F and G. Okay? The parameters that appear inside F and G. Are there any questions? Okay, so now we want to.
You also said that we will see the base manifold is not Calabi-Yau but close to it.
Yes, so here you can see that the base manifold is locally flat, right? Because it's holomorphic, right? So it's locally flat except that the curvature is concentrated at the 4 points, right? So that's orbifold of the torus, right? So that's why the base manifold is not Calabi-Yau. Right? It's you compactify type 2b on Calabi-Yau and then take an orientifold. Right? That's what the base manifold is. Okay, so now we want to study the general situation. That we want to see whether it is possible to interpret a general F theory configuration in terms of orientifolds. Now, in a sense, it should be possible because, after all, once you know that one point in the moduli space of F theory is same as one point in the moduli space of the orientifold, you could deform the orientifold by pulling the difference away from the original location. You can deform the F theory, right? And it better be that the moduli spaces are the same, right? Because as a string theory they are equivalent. Okay? So it cannot be that this has different moduli space compared to that one, right? Because once two string theories are equivalent, okay, their moduli spaces must also agree. So from that perspective, one knows, or one expects that there should be a map between the F theory moduli and the orientifold moduli. Okay. The question is, how do you see this? Now, to see this, okay, one should keep in mind that the orientifold description that we have given, that's a perturbative description, right? The orientifold makes sense to leading order in perturbation theory, and then there will be corrections. Okay. And the description that we have given is valid to leading order in perturbation theory. Right? Once you start including perturbative corrections, everything that you have said about it will get corrected. So if you want to make a comparison between the orientifolds and F theory, okay, we should try to go to a regime, okay, to some corner of the F theory moduli space where we expect the description to be perturbative, right? Which means that you need the coupling constant to be small everywhere on the base or almost everywhere on the base, right? Because only then you expect that there should be a perturbative description, and you can hope to make some comparison between what you see on F theory side and what you see on orientifold side. So how do we make the F theory coupling, the coupling in the F theory description small? We have to make sure that tau is close to I infinity for most of the base. Okay. Now we have this formula J of tau of Z as 4 times 24f cube over delta. Delta is 4f cube plus 27g square. So you want to try to make sure the delta is small almost everywhere, or delta is small almost everywhere, right? Because if delta is small, J of tau is large, and J of tau large means tau is close to I infinity, right? Because J has a pole at tau equal to I infinity. Now of course it doesn't make sense to say for sure that tau is close to I infinity. Tau is close to I infinity or one of its images. Okay. But you can choose to take it to be I infinity. At least J of tau has to be large if we try to interpret this as weak coupling.
Isn't it more convenient to map this infinity to some finite point and then
Map.
and when you talk about weak coupling but not exactly zero coupling, isn't it, does it make more sense to bring that I infinity to some?
See, the point is that the J of tau plane doesn't have a symmetry. Okay, that it's not like SL2. See, there is an SL2C symmetry acting on the J of tau, which gives an equivalence, right? I infinity is a generally different point. See, topologically it has the it's like a sphere, but different points on the sphere are equivalent here. Okay? Because J of tau equal to I infinity is clearly different from J of tau some other point, some other value, right? Because you are asking about whether the coupling is weak or not. Right? That's a physical question. Right? So yes, instead of using g of tau, you could use g of tau plus 1. Okay? In which case, well, if even if you do g of tau plus 1, it will not shift the pole, right? So basically the point is that g of tau, the pole is at tau equal to I infinity. Okay? You can try to use 1 over g of tau, for example. Okay? But it's not that that will make life any easier. Okay? So the fact remains that if you want to make the coupling to be small everywhere, then you need g of tau to be large, and that in turn means that we need delta to be small. Okay? When if delta is small, then this is large, and that means tau is close to I infinity. So to see how to make delta small, let's first see how to make delta 0. Okay? Delta equal to 0 would correspond to 0 coupling everywhere, right? Because J will be infinite. So because delta has this structure, f is a polynomial of degree 4 and g is a polynomial of degree 6, the most general form of f and g which makes delta 0 is f, get the numbers right, so f equal to minus 3h square, g equal to minus 2h cube. Okay, this minus 2 you could have changed to plus 2, doesn't matter. But h is a polynomial of degree 4. Right? Because if you put this, then delta will vanish identity. Right? This will make delta 0. That means 0 coupling. Okay, this in a sense is a special case of what we did earlier, except that this A and B coefficients also we adjusted appropriately to be this minus 3 and minus 2. Okay, otherwise this is a special case of what we did earlier, right? Product proportional to Z minus Z. So we will parameterize. Of course, you don't want that 0 coupling. We want that weak coupling. So what we will do is we will parameterize f and g, okay, by taking these to be starting points and then adding something small. So what we add to f we will call c times eta. Where c is small, this is a small number, and eta is some polynomial of degree 8. Similarly to G also we will add something small. Okay. And here we will parameterize in a somewhat specific way. Okay. We will parameterize it in the following way: C H eta the C square chi. Okay, why we are doing it will become clear later. So chi is a polynomial of degree 8, sorry, degree 12. So the point is that the H, C and eta have already been introduced earlier. Okay, this is not an independent deformation. So what we are saying is that the deformation of G that we will be taking from this minus 2h cube, okay, there will be part which is determined completely by what you have done with here. So why you are doing this will become clear later. But then there is a independent deformation, completely independent. Chi is a general polynomial degree 12, but that coefficient will take to be c square. Is this clear? So this is still a completely general deformation. Right? As long as we allow c to be arbitrary and chi and eta to be arbitrary, okay, it's a completely general deformation of f and g. It's just that we have organized this deformation in some somewhat strange looking way. Okay, that taking the deformation of f to be of order c, whereas the independent deformation that we are allowing for g is of order c square. Okay, and there is a order c dependent deformation, but that's completely fixed.
you're looking at small deformations. So for
C to be small.
For F, you're keeping order C. For G, you're keeping C square. Why is that justified?
No, so this is a complete result. I'm not saying this is an approximation.
So C is not necessarily small.
No, C is small, but it's not that there is something else to added to F.
Why not a C square chi hat?
Well, you can absorb it and redefine eta appropriately, right?
Oh, eta can have coefficients which are small then.
Exactly. Eta can have coefficients which are small or big, right? Right now we are not saying anything about eta. Okay. So, if we allow C to be general, right, then this is the most general deformation, right? In fact, it's a highly redundant way of defining it, because once you specify C and chi, right, these are completely general things, right? This captures everything, right? Is that you are organizing it, so you are using a redundant description, okay, and you are organizing these terms just by writing it in this way, okay? And eventually we will take C to be small, okay? And that's how we will study the weak coupling. Is this clear? Okay, if you allow C to be finite, okay, and eta and chi are arbitrary anyway, then it's a completely general class of deformations. Okay, now it's a straightforward algebra, and
What's the second term CH eta in the definition of chi?
the second term.
CH eta, can't we absorb that in the
Yes, we can. We can, except that because we are taking C to be small, okay, we keep this because this is of order C deformation, right? We take chi of order 1. Okay. So you can observe it in the definition of chi, but then chi has to have an order 1 over C term, right? Right? Which will become big. Okay, we are thinking of that the way we will take the weak coupling limit. So this is a general parameterization, right? Right now we can say C is anything. Okay. But when you want to compare the F theory description and orientifold description, we will do it for small c. Okay, that's how we will take the weak coupling limit. Okay. As long as C is finite, yes, you can do anything that you like, right? You can absorb it in the chi, but we don't want to do it because eventually, in the small c limit, we want to ensure that there is a piece here, okay, linear piece in C. Okay, but like linear piece is not independent linear piece, it's determined in terms of this and the H. Okay, so the reason will become clear soon. So if you calculate delta, which is 4f cubed plus 27g square, okay, this is an exact result, no approximation has been made. This is given by eta square times 4c eta minus 9h square plus 54 times c eta square I plus 27 c square I square. Okay, this is an exact result. You just substitute f and g and calculate delta. Okay, but now we'll see the advantage that we have for c going to zero limit. So this becomes for small c, c square, and inside this we'll keep only the c independent pieces. Okay, because we are taking c to be small, the rest we are taking to be of order 1. So we get minus 9h square eta square plus 54 minus 108 h cube chi. So this is c square h square. So I can also put a minus 9 c square h square times eta square plus
But a small c, both terms, even a c square term should be taken, shouldn't chi be of order 1 by c and then the.
No. Chi by definition we are taking to be finite, right? We are taking the c goes to 0 limit, keeping chi and eta finite.
But then the c square chi should drop the equation for g, isn't it? I mean,
Well, the point is because there is an overall factor of c square, you cannot drop it from the beginning.
yes.
When you calculate this delta,
But then in the definition of f, shouldn't they also add like c square something? I mean, for small c, you are keeping linear terms in one and quadratic in the other. Is it justified or?
no, because this is not an expansion. See what I'm saying is this is the general form. I'm saying that let's take c to be some parameter and take f and g, parameterize f and g this way. I can always choose to do that, right? Okay, I parameterize f and g this way, and now I'm saying that let's see what happens when c is taken small.
So if I wish, I can also add a c cube term.
You could, except that it will mess up things a little bit, right? You could add a c cube term. That you can absorb inside chi, because you are claiming that you will take the c goes to 0 limit keeping chi finite, right? Okay, so yes, you could add some order c cube term in chi, but that is absorbed. That is perfectly okay because you are taking chi to be some finite function, right? So adding an ordered c term in chi is okay. Right? In the c goes to 0 limit, that will just drop out.
So we keep up to c square because somehow we know this is complementary.
No, we don't. We don't. I mean, this is not at this stage. Before you have taken c goes to 0 limit, this is a completely general parameterization. Right? I can say, for example, take any f and g. Okay. Take any f and g. I can choose eta to be f over c, h to be 0, eta to be f over c, and chi to be f g over c square. Right? It's a highly redundant parameter, and I can always choose my eta and chi. So given any f and g, I can always find h. In fact, h also you don't need to find. I can always find eta and chi satisfying this.
You choose it such that the order c term vanished in delta.
Yes. So the c I have put in, okay, as an extra ingredient, okay, because eventually we will define the weak coupling limit from the f theory perspective as the c goes to 0 limit. Right? That's up to us. I mean, how you define weak coupling limit, right? Normally in string theory, you define weak coupling as e to the minus 5 going to 0, right? Or e to the 5 going to 0. Right? Why do you do that, right? So similarly, I have introduced a parameter c, which is completely arbitrary, and now I have a right to define what I mean by weak coupling limit, right? How will you compare to the orientiform? I can put c anywhere I like, right? Okay, this by definition will be the weak coupling limit. Okay, what we will call the weak coupling limit from the F theory perspective. Right? Before you have taken the limit, right, this is a completely general parameterization. I mean, the question you could have asked is if we are using a specific parameter that doesn't cover the full space of f and g, then you would worry, right? Then some part of orientifold is not covered, some part of f theory moduli space is not covered. For a general C, f theory moduli space is completely covered. Okay. Now I am saying that let's see what happens in this parameterization when you take C to 0. Is this point clear? Okay, so this parameterization is completely up to me, right? I have chosen to parameterize it this way. The fact that this parameterization is allowed is clear because I can always find eta and chi for a given f and g.
And for a given c.
Well, C, yes, I mean you can choose, that's why I'm saying it's a highly redundant parameterization, right? That you can use part of C you can absorb in eta, right? For example, you could absorb C into eta C, so the whole thing, right? You could absorb C into eta, you could also absorb minus 3 h square into eta. Right? And here everything you could absorb into chi. Okay? So clearly, I mean for a general C, any C that you like, you can always find a parameterization like this. Okay? The C has been introduced just to describe how to take the limit. Okay? How to take what we mean by the weak coupling limit, because in that limit is where we expect that you can make some connection with orientifolds. Okay?
And this corresponds to weak coupling limit because when C goes to 0, we again get delta equal to 0.
Exactly. Yeah. So it corresponds to weak coupling limit because when C goes to 0, you get delta equal to 0. Okay. So now if you look at this is eta was of degree 8. This was of degree 12, this was of degree 4, and h was of degree 4.
So why does that? Oh, that's okay.
Why does that? It's fine. Okay. So this whole thing is a polynomial of degree 16. Yeah, a generic polynomial of degree 16. So for generic choice of chi and eta, we expect that this will have 16 independent zeros. Okay? In accidental cases, of course, some of the zeros may coincide, but in general, these 16 zeros will be independent. Right? 16 distinct zeros in general. This one, h is a polynomial degree 4, so h has 4 zeros, but because delta has h square, these 4 zeros are actually each double zeros. So what you say is that in this limit, the 24 zeros of delta has organized themselves into 16 independent zeros spread over the base and 4 double zeros. Total number of zeros is still 24. But that you cannot get out of, right? Total number of zeros is still 24, but they have organized themselves into 16 independent zeros and 4 double zeros. Now the fact that this is a double zero is an artifact of this limit. Okay, if we didn't take the c goes to 0 limit, then of course this is a generic. This one has no factorization property of that kind. Right? This is a generic polynomial of degree 24. So here all the zeros are separate. It's only in the c goes to 0 limit that the zeros have organized themselves into 4 double zeros and 16 single zeros. Is this clear? And so what we will see, okay, so let me state the result first and then we will try to prove this. Okay. So what we will do next, okay, is to calculate the monodromy around each of these zeros. Okay, we will calculate the monodromy around each of these 16 zeros and the monodromy around the double zero. Okay. We will see that the monodromy around each of the 16 zeros, okay, is the same as the monodromy around the D7 plane. Okay. And the monodromy around each of these double zeros is a monodromy around the non-uniform plane. Okay. So that's the way F theory makes its connection to orientifold planes. Okay. Namely that even the F theory at a generic point in the moduli space has 24 zeros, okay, and in this limit, in the weak coupling limit, these 24 zeros organize themselves into 16 single zeros which are the positions of the D7 planes and 4 double zeros which will identify as the positions of the orientifold planes.
This square of h square then corresponds to the fact that orientifold looks like 2 objects.
Yes, exactly. Okay, this because it's a double zero. So you, of course, you know from the orientifold viewpoint, you don't know that it's two objects, right? You only see the orientifold. Okay. But from the F theory perspective, okay, it is indeed 2 objects because if you didn't take a weak coupling limit, right? Now you can make corrections of order C, include corrections here. Okay, because this is an approximation, right? Once you go back to this, each of these double zeros will actually split into 2 zeros. Is this clear?
Can this result be right that with a different parameterization of the perturbation around F and G?
Well, you could change things a little bit, right? But not arbitrarily, right? Because I mean, you expect to arrive at this parameter only if you take the weak coupling limit property, right? Not every limit of F theory will give what you say in
So
orientation.
if I in the G, if I just take some polynomial chi into c square and get rid of this ch eta.
Yeah, I think if you get rid of the CH theta, the organization will be different. Right? You need this CH theta term to get this structure.
So
So this ultimately means that the F-theory picture is more general than the orientifold picture because C can be arbitrary.
In a sense, yes, except that even from the orientifold picture, right, you can of course carry out perturbation theory, right? Because, from the orientifold picture, the orientifold is only the leading order in perturbation expansion, right? And the string theory tells you how to systematically calculate corrections. Right? So in this sense, from orientifold also you can do these corrections and see what's going on. Right? F theory picture is more general in the sense that it for example immediately will solve the problem that is he saw in orientifold, that if you really take the orientifold plane, right, then tau going to minus I infinity at the core, right, which you know is nonsensical, right? So orientifold plane, we knew at that stage itself that it cannot be a valid description of the solution all the way, right? F theory doesn't have such problems, right, because F theory gives you directly J of tau, right, and J of tau for any complex value of J of tau, you can find a point called image in the fundamental domain, right? So in that sense, F theory gives a complete solution for tau. Orientifold doesn't give a complete solution. We know by looking at the solution that there is something wrong near the orientifold plane, right? And that's what F theory corrects. Okay? But if you want to do, say, scattering amplitude calculation, right, it's easier to use orientifold description because you have a perturbative description, right? F theory doesn't have a perturbative description because generically the coupling becomes large in some part of the base. Right? So the two things have different roles to play, right? Some things are geometrically easier to see from the F theory perspective. In particular, as I said, enhancement of gauge symmetry to exceptional gauge groups, right? That's very hard to see from the orientifold perspective. You can see it in F theory. Okay? But if you actually want to do some perturbative amplitude calculation, it's much easier to use orientifold description, right? Where you have a systematic string perturbation theory. Is this clear? Okay, so today we will not go very far because there is a thesis difference starting, but let me just do one thing. Okay, so I'll try to calculate the monodromy around these zeros, okay, because this is a little easier. Okay, so if you look at J of tau, first you have to choose a convention for tau. So J of tau is 4 times 24 cube. Okay, now I'll put the expression for F C eta minus 3h square on cube over, let me write the approximate sign because we use the approximate form for delta, so c square times minus 9 c square h square times eta square plus 12h square. Now, the fact that c square is in the denominator makes this J of tau large almost everywhere. Okay? Almost everywhere. Why almost everywhere? Because the denominator can be 0. The numerator can be 0, right? There J of tau is not large. Is this clear? If this becomes small, then of course the c square doesn't help in the numerator, right? So, what we need to do is to, if we exclude the region, if mod h is much larger than,
There shouldn't be a minus sign.
pardon?
Minus, there comes a minus.
This is plus sign?
No. I mean, overall minus sign should be upstairs also. So, because you defined f to be minus 3h squared plus c eta.
Yes.
And j of tau was defined 4
F cube.
Yes.
So minus 3h square is still there. Yes, so when you take it out, it will become plus.
Yeah. Okay, it's alright.
Right?
So,
Okay, so let me say it in the following way. That you see C is small. Okay, so this can become small near the zeros of H. Right? So what is the picture? So let me draw this. So let me draw the squares at the zeros of H. Okay, 4 of them, and 16 crosses which are the zeros of the other ones. Okay, so 16 of the zeros of this and 4 of the zeros of H. Okay. So the point is that if we are away from the zeros of H, okay, let's take some finite radius around this. Okay, we are assuming that these are far away, so that it makes sense to enclose them by some finite area circles. Okay, if you are away from the zeros of these, then tau is large everywhere. Is this clear? Well, then J of tau is large everywhere. Okay? Because you see, once you are away from the zeros of H, right, that means C of course is small. So this numerator is not becoming small, and there is a C square sitting in the denominator. So we are in business. Okay? So that means that except for inside these shaded regions, except for inside the shaded regions, tau is large everywhere. Is that clear? Well, J of tau is large everywhere, which means I can choose tau to be close to I infinity everywhere. Okay, so J of tau large means tau can be either close to I infinity or any of its images. Right? That's completely my choice. Okay, but I'll declare that tau is close to I infinity everywhere. Okay, because it's of course itself is equivalent to the other cases, but since we are using the tau 1 over tau 2 as my coupling constant, okay, it pays to have tau to be large everywhere, tau 2 to be large everywhere. Okay, so I know from this that J of tau is large almost everywhere outside the shaded regions, and I use that to choose my convention that tau 2 is large everywhere.
So H is not close to 0.
Yeah, so we are making sure that H is the zeros of H are avoided, right?
How did you argue that J of tau is large?
Because then this numerator is finite as long as you are close from H equal to 0, right? This is finite or small, okay, and there is C sitting downstairs, right? Because of this C.
No, but we are away from zeros of H.
Yes, so which means that the numerator
Can be small.
no, it's large away from the zeros of H, right? So numerator is finite.
C is smaller.
C is small, yes. So C is small. Okay. So as long as you are away from the zeros of H, the numerator is finite. Right. This is of order 1. Sometimes it can go to 0 also. Okay, which is even better. Right. If it goes to 0, you are helping it to become large. Okay. But even if this is not 0, even if this is finite, because there is a C sitting there, it makes the whole thing large. So everywhere except inside these disks, tau 2 can be taken to be large. Okay? And because tau 2 is large, okay, it fixes the structure of the monodromy, okay, to be, so monodromy outside the shaded region is of the form plus minus t to the n. So t is just 1 1 0. Why? Because any other SL2Z transformation,
What is the tau t power?
t to the power n, plus minus t to the power n, where n is some integer, could be positive or negative, and t by definition is this number. You see, the point is that any SL2Z transformation, okay, suppose you start from tau to large here, okay, then you go around the path which is completely inside this region, okay, you don't enter the shaded region, then tau 2 remains large everywhere, okay, when it comes back, okay, it starts from large, remains large everywhere, comes back to the original point, it's large. So the monodromy can only be a multiple of this, because any other SL2Z monodromy will take a large tau 2 and take it to finite tau 2. Then AZ plus B over CZ plus A tau plus B over C tau plus D, right? Okay, you can easily convince yourself that unless it's such translation of tau, the tau 2, large tau 2 will go to finite tau 2 or even 0 tau 2. In fact, large tau 2 will go to close to 0 tau 2.
Like we shouldn't have tau in the denominator. In that tau goes.
Exactly. Yeah, because tau 2, okay, I can write down the, so under tau goes to AZ plus B, sorry, A tau plus B over C tau plus D. Tau 2 goes to tau 2 over C tau plus D mod square. So if tau 2 has to remain large, then C should be 0. Right? So this means the C should be 0. And if C is 0, then AD minus BC equal to 1. Tells us that A and D must be 1. Well, A equal to plus minus 1 or D equal to plus minus 1.
Okay, I'm trying to visualize this in the Poincare disk representation, the upper half plane. Now, in that case, large tau means that we are basically close to
I infinity.
I infinity. Like in general, using translations of this sort, you can't bring it. You can't bring it to any other rational point.
Exactly.
You see, but what if you take n to be extremely large and then you take it to a rational point which is around that I infinity on the disk.
Well, even if you take n to be extremely large, right? I mean, n is finite after all, right? However large and finite it is.
So we are taking tau to be actually infinity, or not just something very very
No.
large.
So the point is you see the monodromy will not change by continuous variation of tau, right? Okay, tau you can change by C. Suppose the monodromy is something. Okay, you postulate that is a SL2Z monodromy. So that monodromy is not going to become suddenly some other monodromy, right? Now you take that and then take the limit when C goes to 0.
Okay.
Right? The monodromy is not going to change, n is like going to be fixed. Right? And in that process, you drive this to tau equal to I infinity again. Okay? So n we are thinking of as a finite number, right? Finite, it may be large but fixed number. Okay. So this already simplifies things a lot, because this says that if we are going to identify these as D7 planes and these as O7 planes, okay, we have already passed our first test, okay, because on the orientifold plane, okay, if you remember, okay, the monodromy around the D7 plane was, so D7 plane monodromy was 1 1 0 1, okay. O7 was minus of 1 minus 4 0 1. Both of these monodromies are of this kind. Okay, so at least it's not totally crazy to think of these as orientifold planes and these as G7 planes. Okay, because we have established that the monodrome is around all these points, all these 16 plus 4, okay, 16 regular points and 4 double zeros. They all have this structure.
How do you say that around zeros of each the monodrome is of?
Because we go like this.
But then there is a restriction, I cannot go close.
No, you are not going close. That's exactly. So if you go close and if you go in between two of the zeros, right? Each zero actually is two zeros, right? If you go close and pass through the two zeros, right? Then this argument doesn't work. Because you are entering a region, right, where tau has become of order 1. Okay, you have to stay fully inside the weak coupling limit, right?
So the 16 zeros should be far up.
Yes, so you are assuming a generic situation where these have all distinct zeros, right? And H has distinct zeros. Okay? And with that understanding, this picture holds, right? If some things coincide with something else, then of course things can be more complicated, right? In fact, I mean the reason that we get these exceptional groups is precisely when these zeros are not apart but they coincide in a strange fashion.
Plus minus t to the n or plus minus t goes to the n? Because how do you get this relative sign between 1 and minus 4? If you just take t to the n and...
No, n can be positive or negative. So this is 1 minus 4, 0, 1 is t to the minus 4.
How do you okay, you take inverse of t to the 4.
Yeah, take inverse of t and take raised to 4 power.
Okay, there's a question more of the weak coupling limit.
Yes.
Rather than this actually. Like physically, the weak coupling limit basically means that we are, the torus is being stressed out, right? In some sense.
Yes, that's right.
So, from a physical point of view, it shouldn't matter if tau is I infinity or any of the other cusps.
True.
So
You could have formulated the whole thing, right, in terms of its SL to Z conjugation, right? Then you will say instead of having t to the n, right, it will be some s inverse to the power n, right? Where s, instead of you saying that tau is I infinity, close to I infinity everywhere, tau will be close to one of the other images everywhere, right? So that is certainly allowed, right? Because nothing tells you whether tau equal to I infinity is the point or whether tau some other value of tau is the point, right? Because you only know g of tau. But we are choosing a convention, right? It's a purely convention dependent description. We are choosing a convention where we say tau equal to I infinity, because that's what we mean by weak coupling normally.
Because it's, I'm finding a bit strange because like all these are physical equivalent, but from a convention you're actually able to draw something physical out, like the monodrome. Like just by convention you're able to draw.
Yeah, no. The point is that from the convention we are not. If we use a different convention, we can still draw something out, right? All you will say is that instead of monodrome being t to the n, it will be s inverse to the power n, right? Where s is some fixed matrix.
Something else.
Yeah, s is something else. And s is that object which has taken from I infinity to wherever you are putting these things in, right? So the fact that tau remains almost constant, right, either close to I infinity or close to some other image of I infinity, that follows from this argument. Right? Now the fact that you have chosen it to be I infinity is our choice, right? Because you want to make connection with weakly coupled orientifold planes, right? Which is normally described for weak coupling, right? Which is tau goes to I infinity. In fact, I mean, orientifold planes were discovered much before the SL to Z duality was discovered, right? So in that sense, that time we didn't know that tau equal to I infinity is the same as tau equal to something else, right? Tau equal to its image. So you want to make connection with that picture, right? Where weak coupling is really something special, and that's how you have chosen to take tau equal to I infinity in the intermediate regions. Yes.
How do you know going around the orientifold plane will give t minus 4?
No, that we don't know. We already know, so far we have already said it's plus minus t to the n from the F theory perspective, but now I am saying that from the orientifold perspective we have computed these monodromies, right? And there you know that d plane carries 1 unit of charge, that's why the monodrome is 1101, that is t. And orientifold planes carry minus 4 units of charge, that's why it's 1 minus 401. but then you have an extra minus sign because of this minus 1 to the f left times omega transformation that you make when you go around the orientable plane, right? That's why you reverse the sign. Okay, so that's where you will try to get to. Right? That's the goal. That's what we want to prove. Okay. So far, all you have said is that from the F theory perspective, we know that the monodromy is of this kind, right? Plus or minus t to the n. Right. So next time we will determine the monodromy is around each of these zeros, okay, and also each of these zeros, and then show that indeed they are the same as what we got for these 7 branes in orientable planes. Yes.
Can you repeat why J was independent of Z before adding the perturbation?
Oh, before, so when you C equal to 0.
Yeah.
Oh, see the point of for the general case, we took this general form F as A H square, G as B H cube, right? Okay, A and B are constants, H is some polynomial of degree 4 of this case. In this case, G of tau of Z, this formula was 4 times 24F cube over 4F cube plus 27G square. And this just becomes 4 times 24A cube over 4A cube plus 27B square. Okay. So A and B are just constants. So that's why G of tau is constant and hence tau is a constant on this case. Yes, that was the case when the D branes are on top of orientable planes, right? That's the identification you made there. Now you are considering a more general situation. Okay. But the point is that to be able to compare this more general situation with what we had seen in orientifold, okay, we have to take a weak coupling limit. Right? We cannot hope to take a most general F theory compactification and then make connection with what you saw in orientifold. Because orientifold description is a perturbative description. So only you can hope to expect that if in the F theory you manage to keep the coupling small everywhere or almost everywhere, okay, then you can make some connection with orientifold. Okay? And in fact, the point is you cannot really make the coupling small everywhere, okay, and that's where the F theory description differs from the orientifold description. Inside these, okay, when you are close to the singularities of H, we have seen from this formula that we cannot keep the coupling to be, the coupling does become order 1, okay, and it's this order 1 effects, right, which are eventually responsible for orientifold not being really a single point but actually 2 separate zeros. Okay, so I think I'll continue tomorrow.